In this video, we're going to take a look at the binomial distribution. The binomial distribution is for discrete data, and as the name suggests, there are only two possible outcomes. One is a success and one is failure. You would think that just because there are only two possible successes, it would limit what it could be used for. But let's take a dice. If you roll a dice, there are 6 possible outcomes. 1, 2, 3, 4, 5, 6. And you would think that you could not use the binomial distribution to calculate probabilities if you are dealing with a dice. But you can make it into 2 possible outcomes. Say you are interested in the number of 6s obtained when you roll a dice many times. The 2 possible outcomes could be 6 or not 6. That would give you 2 possible outcomes. So you could use the binomial distribution when dealing with a dice. The binomial distribution has specific rules that have to be followed when you are using it. And these are the rules. The number of trials must be fixed. What we mean by that, if you're dealing with the dice, let's go back to the dice, you must roll it 100 times. That is a fixed number of trials. Each trial must have the same 2 possible outcomes. So, go back to the rolling of the dice analogy, 6s or not 6s. The trials must be independent. That means each trial must not affect another trial. And the probability of success must be the same in each trial. So none of the probabilities must change. If a distribution or a scenario passes all 4 trials, you can use the binomial distribution. If only one of them does not apply, the binomial distribution cannot be used. When we are using the binomial distribution, we write it in this specific way. Capital X, or any capital letter, stands for the random variable. The squiggly line means is distributed as. The B stands for binomial, and then in a pair of round brackets, we have 2 things. N stands for the number of trials, and P stands for the probability of success on each trial. So we write down the probability of success, and these are called the parameters of the binomial distribution. Now we're going to go through some questions. The first question is to check whether we understand the parameters that allow us to use the binomial distribution. So question 1, say whether the following are examples of a binomial distribution. A coin is tossed 10 times and X equals the number of heads. So let's go through each individual parameter and see if it applies to the binomial distribution. So a coin is tossed 10 times. X is the number of heads. So we're interested in how many heads come when we toss a coin 10 times. So yes, there is a fixed number of trials. Each trial has the same 2 possible outcomes. Well, yes, the possible outcomes are heads or not heads. Are they independent? Well, yes. When we toss a coin, each coin is independent of the other. It doesn't affect each other. And the probability of success must be the same for each trial. Yes, the probability of success is a half in each case. So yes, we can use the binomial distribution for this particular scenario. The second scenario, 10 cards are drawn from a pack without replacement. X is equal to the number of kings. Well, let's have a look at each of the parameters. The number of trials is fixed. Well, yes, the number of trials is fixed. There are 10 of them. Each trial must have the same two possible outcomes. Well, yes, they are. You either get a king or you don't get a king. The third, the trials must be independent. Well, because the cards are not replaced after they've been picked, the trials are not independent. So in this case, you cannot use the binomial distribution because the trials are not independent. And the third scenario, 100 people are chosen at random. X equals the number who say they have voted Labour. So let's go through the four parameters. The number of trials are fixed. Well, yes, there's 100 people that have been chosen. Each trial must have the same outcome. Well, yes, they've either voted Labour or not voted Labour. The trials are independent. Well, yes, the trials are independent unless you put all the 100 people into a room and let them speak to each other. As long as the people are chosen at random, it is independent. The probability of success must be the same in each trial. Well, yes, the probability of voting Labour doesn't change because the people change. So in this scenario, yes, you could use the binomial distribution. Question 2. A biased coin is flipped 10 times and the number of heads is recorded. If the probability of getting a head is 0.8, let x equal the number of heads. Find A, the probability of x equaling 6, B, the probability that x is greater than 7, C, the probability that x is less than or equal to 4, D, the probability that x is greater than or equal to 5, E, the probability that x is less than 1, F, the probability that x is between 3 and 8, G, the expected value of x, and H, the variance of x. If you look in your formula booklet, you are given how to write the binomial distribution. X belongs to B with parameters n and p. You are told that the mean, the expected value of x, is equal to np, and you're told that the variance, VAR of x, is equal to np 1 minus q. I always like to write 1 minus p as q. So in A, I want to find the probability that x is equal to 6. In other words, I want to find what is the probability when I flip this coin 10 times of getting 6 heads. 6 heads exactly. Well, I could get head, 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 tail, 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 tail. That's one possible outcome. Or I could get tail, 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 head, 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 head. That's another possible outcome. Or I could get head, 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 tail, head, tail, tail, tail. Flipping a coin 10 times, there are loads and loads of different combinations that I could get. In fact, there are 10, choose 6 different ways I could get 6 out of 10. And then I would have head to the power of 6, tail to the power of 4. So this is actually that is a way of me calculating the probability of getting 6 heads and 4 tails. If I wrote that formally as a formula, I would get n choose r, p, which is success, to the power of r, q, which is failure, to the power of n minus r. And that is the formula for calculating the probabilities of a binomial distribution. But luckily, we don't have to use the formula. We're allowed to use our GDC. On the TI Inspire, there are 2 functions that allow you to calculate the probabilities for binomial distributions. There's the binomial PDF, which allows you to calculate single events, like the probability of getting 6 heads, or there is the binomial CDF, which allows you to calculate the probabilities of, say, x is greater than 7, which means the probability of getting 8, the probability of getting 9, the probability of getting 10, all added together. So there is a range of values for the binomial CDF. We will go through each one separately on the calculator so you know how to input your data. For each of these questions, as we go through it, I will write down underneath whether you need to use binomial PDF, which is for single values, or CDF, which is for a range of values. If it's PDF, I'll write down the value of X. If it's a CDF, I'll write down the lower bound and the upper bound that you need to put in to the calculator. For one question that needs PDF, I'll show you how to do it on the calculator. And for CDF, I will also show you how to do it on the calculator. So for the first one, the probability that x equals 6. Well, we're going to use binomial PDF. So x is equal to 6. So let's get our GDC out and show you how to do it on the calculator. I've opened my TI Inspire to a calculator page. So I go to menu. I want 5 probability. I want 5 distributions. And now if you scroll down a little bit, A is for binomial PDF, B is for CDF. In this case, we want PDF because it is for one single value. So if we open that, we get this. It tells you that it's binomial PDF at the top. And in this case, we want the number of trials. The probability of success in this case is 0.8. And we want the X value that we require. So we want X to be equal to 6. If you then press OK, the probability of getting 6 heads with a probability of 0.8 for each head is 0.08808, which is 0.088 to 3 significant figures. The answer is 0.088 to 3 significant figures. B is the probability of getting greater than 7. So in this case we want CDF, and the lower bound, because it is greater than 7, 7 is not included, so the lower bound is equal to 8, and the upper bound is equal to 10. So I will now go back to the calculator and show you how to do a CDF. I've reopened my TI Inspire, so I go to menu, 5, scroll down, open binomial CDF, and this time I get 4 things to fill in. So number of trials 10, success is 0.8, my lower bound is 8, my upper bound is 10, press OK, and the probability of getting greater than 7 is 0.678 to 3 significant figures. So write down the answer, which is equal to 0.678 to 3 significant figures. Part C, the probability of x being less than or equal to 4. Well, again, there's a range, so you're going to use CDF. The lower bound in this case is 0. The upper bound is 4 because 4 is included. So now if you go do that on the calculator, you get a probability that is equal to 0.006 to 3 significant figures. Part D, the probability that x is greater than or equal to 5. Well, again, it's CDF, and the lower bound this time is equal to 5 because 5 is included. The upper bound is equal to 10, and if you put that into your calculator, you will get 0.994 to 3 significant figures. Please note that the answer to question 4 and question 5 add up to 1 because in those 2 questions all possible outcomes have been included. Part E, the probability that x is less than 1. Well, that is the same as the probability that x equals 0. So in this case, you would use a PDF. And in this case, you would expect a very small number, and it is. And the answer is 1.024 times 10 to the power of minus 7. A very, very small number. Part F, the probability that x lies between 3 and 8. And if you look at the inequality, 3 is not included. So the lower bound, so you use CDF with a lower bound equal to 4 and an upper bound equal to 8 because 8 is included. And that gives you a probability equal to 0.623. Part G, you're asked to find the expected value of x. Well, this is equal to, you're given it in the formula booklet, NP. Therefore, the expected value of x is equal to, well, the number of trials is 10 times the probability of success is 0.8. 10 times 0.8 gives you a value of 8. The final part of this question is to find the variance of x. Well, that is equal to NPQ. Therefore, the variance of x is equal to, well, n is 10, success is 0.8 times 0.2, so which is equal to 8/5, which is equal to 1.6. These questions will normally come in paper 2 on a calculator page. You still need to be aware of the formula though. So the formula is n choose r, p to the power of r, q to the power of n minus r, and remember q is equal to 1 minus p. So if they do appear on paper 1, they very rarely do. You'll need to use the formula. If your calculator runs out in an exam, you need to use a formula, so please be aware that it does exist. Question 3. 2 fair dice are rolled and the numbers showing on the dice are added together. This is done 15 times, and the number of times the sum is equal to 2, 7, or 11 is recorded. Let x be the discrete random variable representing the number of times that the sum is equal to 2, 7, and 11. A. Find the expected value of x. B. Find the probability that x is at least 2 but not more than 6. So for A, to find the expected value, first we need to find the probability of getting 2, 7 and 11. And in order to do this, I'm going to draw a sample space for the 2 dice. Using the probability sample space, the probability of getting a sum of 2, 7 or 11 is equal to 9 out of 36, which is equal to a quarter. So now, x is binomial. There are 15 trials, and the probability of its success is a quarter. So my expected value of x is equal to NP. So my expected value of x is equal to 15 times 1/4, which is equal to 3.75. Part B. Find the probability that x is at least 2 but not more than 6. So I want the probability of 2 being less than or equal to x being less than or equal to 6. So I'm going to use CDF, where the lower bound is equal to 2, the upper bound is equal to 6. And if I use my calculator to calculate that, I get a probability of 0.863 to 3 significant figures. Question 4. In a restaurant, it is known that there is an 8 out of 15 chance that a guest will ask for water with their meal. A random sample of 25 guests are sampled. A. Find the probability that Part 1. Over half of the guests ask for water. 2. Between 24% and 92% inclusive of the guests ask for water. So the first thing we need to do is let W equal guests who ask for water. Then we have a binomial distribution where W belongs to binomial, where there are 25 trials and the probability of success is equal to 8 out of 25. So for part 1, we want the probability that W is greater than 12.5, because that is how many people is half. So that will give us the probability of 13 is less than or equal to W is less than or equal to 25, which when you go to the calculator gives you a probability equal to 0.632 to 3 significant figures. For part 2, we need to work out 24% of the guests, which is equal to 6, and we need to work out 92%, which when you work it out comes to 23 guests. And now we want the probability of between 6 and 23, which when you work it out on your calculator gives you a probability of 0.999 to 3 significant figures. Part B. A second random sample of 100 guests is selected. Let X be the random variable that represents the number of guests that ask for water. Find the smallest value of n such that the probability that X is less than or equal to n is greater than or equal to 0.95. Well, this is a reverse binomial. We know what the probability is. It's 0.95. We have 100 guests. The probability hasn't changed. So we've got a new probability where X belongs to a binomial distribution, where the number of trials is 100 and the probability of success is 8 out of 15. So we can use our calculator to find out how many guests will give us a probability of 0.95. We use reverse or inverse binomial distribution function on our calculator, and that will tell us the value of n. I've opened my TI Inspire at a calculator page, so I need to go to Menu, 5 Probability, 5 Distributions, and if I scroll down, there I have inverse binomial. So the cumulative probability is 0.95. The number of trials is 100. The probability of success is 8 divided by 15. I press OK, and that tells me that the number of people will be 62. That will give me a probability of 0.95. So if I write down my answer to B is n equals 62.